let's talk about angular momentum. Angular momentum is nothing more than the rotational version of momentum. Just like previously, we have seen angular displacement, angular velocity, and angular acceleration as the rotational equivalents of displacement, velocity, and acceleration. So here, angular momentum is the rotational version of momentum. We denote it with a capital letter L, and it is a vector quantity, just like regular linear momentum. Any object that rotates relative to a reference point will have angular momentum. And we define angular momentum as follows. For a point particle, the angular momentum is a cross product of r and p, r cross p, where r is the position vector of the particle, namely r is the vector drawn from the origin to the particle, tail on origin, head on the particle, and p is just the linear momentum of the particle, mass times velocity. Just like with any other cross product, we can calculate the magnitude using the magnitude sine theta formula, or the perpendicular component times the rest. Then you can find the direction by the right-hand rule. That's one way that you can compute it. Just a brief reminder here, when we are using this formula to calculate the magnitude of the cross product, you need to imagine drawing the two vectors and moving them about so that their tails are emanating from the same place, as shown in the figure above. Then, the smallest angle between them, the angle that's less than 180 degrees, is theta. So that's theta in the formula. Then you just take the magnitude of r, the magnitude of p, and then multiply by sine of that angle in between them. Alternatively, you can use these formulas that look at perpendicular components. The magnitude is either the perpendicular component of r to p times the magnitude of p, or it is the magnitude of r times the perpendicular component of p to r. As a reminder of where this comes from, note as follows. Here I have the perpendicular component of r to p, and it is equal to r sine theta. And so we can group the two terms together and thereby form our formula, r perp times p. Similarly, you can convince yourself that p sine theta will give you the perpendicular component of p to r. All three of these can be used to calculate the magnitude of angular momentum. They will all give the same result, and we'll see some examples in later videos of when one might be more useful than the other. Alternatively, you can calculate the cross product directly from the r and p vectors, the position vector and momentum vector, linear momentum vector, by using the determinant method, as you have seen with other cross products. As a reminder of how to do that real briefly, you take your r and p vectors and put them into a 3x3 determinant as follows. And on the top row, you will have your unit vectors for the x, y, and z directions, I hat, j hat, and k hat, respectively. And when evaluating a 3x3 determinant, you can use the cover-up method to see that it turns into a sum of 2x2 determinant. And when you evaluate all those 2x2 determinants, you get as follows, which is the real definition of the cross product. A 3x3 determinant is just a way to remember it. A note about the definition of angular momentum now. The value of angular momentum will depend on your choice of origin. Remember, your choice of origin is arbitrary. You can choose the origin to be wherever you want to be. But because this r vector, this position vector, is in the definition of angular momentum, your angular momentum necessarily depends on the position of your particle, which depends on your origin. So that's very interesting. Let's run a brief calculation to see how this works. Suppose we have a point particle moving about in uniform circular motion. So its tangential speed is constant. We therefore have, for the value of its momentum at this particular moment of time, at which I have drawn the point particle at that particular position in the circle, where v is the velocity of our particle at this particular position at this moment of time. All right, so now we want to calculate angular momentum. To do that then, first we have to define an origin. One good place to put the origin is the obvious place. We'll put it at the center of the circle. All right, so if we do that, what is the position vector? The position vector r is a vector drawn with its tail at the origin and head at the particle. Because the velocity is tangent to the path of the circle, velocity and the position vector are perpendicular to each other. This means the magnitude of angular momentum is simply just the magnitude of r times the magnitude of p. If the radius of the circle is big R, then the magnitude of the position vector is big R. And there we have it, the angular momentum. If you're a little bit confused about that, just remember that sine theta will be 1 because the angle between the radius vector and velocity vector is 90 degrees. When I draw the two vectors so that they're coming from the same origin, you see that the angle between them is still 90 degrees. Just imagine sliding the v vector down so that way its tail is coming from the same place as r. And there you go. Theta is 90 degrees, sine of 90 is 1. So the magnitude of angular momentum is r times p. How about the direction of angular momentum? Well, by the right-hand rule, I point my fingers in the direction of r and curl towards v, and you'll see that my thumb is pointing out of the page. So by that method of using the right-hand rule, and you can use any method, as a reminder, they'll all give the same result, angular momentum is pointing out of the page. So if I make my positive z direction out of the page, then I will say as follows, that. Or if you want, you can just write out of the page. Sometimes another shortcut is just to write that symbol to note that the vector is coming out of the page. It's up to you. In any case, that is our angular momentum vector. All right, well, what happens if we change our origin? Same particle, same position in the circle at the same moment in time, but now let's move our origin to B, where the particle currently is at. Okay, so what's the angular momentum of our particle at this moment in time using this origin? Well, the r vector is the vector that goes from the origin to where the particle is at, which is 0. It's the 0 vector because it is where the particle is at. Our momentum, our linear momentum, our p vector is still the same, still mass times velocity, but it doesn't matter because when we go to take the cross product, we are multiplying the 0 vector with p, and so we end up with the 0 vector. Magnitude of 0 and direction not really anywhere. So there is no angular momentum at this moment in time if we move the origin to where the particle is at. Now, of course, this is a bit silly to do, and we would never do it, because if you put the origin there, the angular momentum of your particle is going to change as it moves around the circle. So at this moment in time, if my origin is over here where it originally was, my r vector is as follows. And you'll see I'll have a different r vector for different points of the path as the particle moves in a circle. Also, this r vector, as it is changing, it's changing as a very complicated function. That makes it very difficult to calculate the angular momentum of the particle as it's moving about in a circle by placing the origin at a point where the particle was at for one moment of time in its motion. By contrast, if I move my origin to the center of the circle again, the angular momentum will be a constant. Wherever the particle is at in its motion around the circle, it has a uniform speed, so the magnitude of v is the same. Its mass stays the same. The direction of its momentum changes, but so does the direction of the r vector, so that you end up, when you calculate it, with L equals big R mv in the z direction, coming out of the page, no matter where the particle is in its path on the circle. So as you can see, choosing your origin, just as with your linear motion problems that you've had earlier in the course, can make your problem simpler to solve or harder. Therefore, choose the origin to make things easy. The best place to choose your origin is to use your common sense on what point you think a particle is rotating about. So if a particle is moving in a circle, it makes sense then to think of it as rotating about the center of the circle. And more generally speaking, it'll be a good idea to put the origin at the center of mass, as we will see. Or another way to put it, if you have a point of symmetry in the motion of your object as it moves, place your origin at the point of symmetry, and that tends to make it easier to calculate your angular momentum.